Hi there, welcome to the lecture Buffer Overflow Revisited. So at a very high level, you now know how the buffer overflow works. Also, you've seen some simple attacks that show you how the principle of local attacks works. And presumably you've watched my lecture on assembly, or you are already an expert on x86 64-bit assembly on Linux. Now, if you haven't watched the lecture and you're not an expert on x86 64-bit assembly on Linux, please watch it after all, because you will be needing it to understand some of the stuff that we'll find later on. Okay, now let's get started. So, we're going to be discussing more sophisticated attacks now. So the simple attacks did not require that you understand the system's inner workings. So they were nice, but they weren't very advanced, and they are not as widely applicable as the attacks that we'll be discussing now. For the more advanced attacks, we really need to understand how the computer runs programs. So, we've discussed part of this in the assembly lecture, and we'll go into some more details showing how the way that the programs are run allows you to attack them, and go into the details of how to do a front-to-back exploit. So, this is where we left off on the topic of buffer overflows. We were able to override some data in memory using a buffer to go over into the frame pointer as well as the return address. Then we wrote some text there and it caused the program to crash. Now, this is not a very useful attack in general. We don't really want the program to crash. We want it to execute the stuff that we as an attacker want to run in the privilege level that the program has. So we need to make it do something useful. We already said, well, simply override it with a return address. But it's not really that easy. We need to find a way to reliably run code and to know which return address to write where. So, at the high level, this is how the attack works, but actually doing the attacks does require low-level insights. And we're going to get these low-level insights now, especially that we also know about assembly. So, questions. How to find exactly where the return address is stored, where to actually return to, and having this information, how are we going to actually attack this perform the attack using this information. So, this applies to buffer overflows, but the exact same questions you get when you do more advanced attacks. So buffer overflows are very common and relatively simple to exploit, but we're going to discuss a bunch of more attacks that are also very useful, more complicated, but still the core insights are the same. So, also of course, we don't intend you to just break systems. We're intending you to eventually write programs and protect systems. So this is also something you will need to know to be able to defend against these. And later in the course, we will be discussing defenses, which also require these same low-level understandings that we'll be teaching now. Now, so far, we've looked at C source code, and we incorrectly assumed that you can infer the stack layout from that. Now, if you've watched the lecture on assembly, you've already seen some surprises. Stuff like padding, for example, or parameters being stored as local variables. In the general case, we cannot predict the stack layout from C code. It depends on the platform as well as the compiler and potentially even the compiler version. Moreover, if optimization is enabled, even the context matters. So the compiler might decide, for example, whether or not it wants to use the base pointer, which changes the layout of the stack frame. So, the stack layout cannot be fully predicted from the C code. So what do we do instead? Well, we did not include this lecture on assembly for nothing. You're going to read assembly code to understand how the stack frame is laid out. So, additionally, even if you know where the return address is, you also need to know how to find it when overflowing your buffer. So, we know where the return address is. In fact, without optimizations, it's always in EBP +8. So that's easy to know. But we also need to know where the buffer actually is. And this is something we will infer from the stack layout. if we know the location of the buffer and we know the location of the return address, only then can we compute by how much we actually need to overflow the buffer. So you could of course simply try multiple inputs. I know students actually do this in the practical that comes with the application security lectures. But it's much more interesting to try and understand how it works. You can make an attack that's much more stealthy, not crashing the system time after time. And sometimes you may actually need to do it like this. So if you're attacking a system that will crash and not reboot when you put the wrong input into there, then you also need to be very careful to make sure not to crash the system. So let's try and see if we can attack this, not by brute force, but by understanding what is happening. In the listing, the vulnerable call is easy to identify. The name of the function that's called in the library is simply visible, string copy, and we see a call instruction directing to it. So it's very easy to find the vulnerable call in assembly code if we know where it is in C. Now the question is, where do the arguments come from? So there were two arguments. The first is the destination and the second is the source of the string copy. Now, if we remember from the assembly lecture, then we know that the RDI register is used to pass the first argument and the RSI register is used to pass the second argument. So this doesn't give us a lot of information yet, right? We see here RAX and RDX. So which are the values loaded into those registers? Well, we just need to look a little bit back and see, for example, RDI, which is the interesting one because this is the target that we're going to overflow. So if we look at RDI, it's loaded from RAX. So we look back to the last time that RAX was written in the assembly code. And we find on line 69A that there's a LIA instruction loading RAX. Now obviously the LIA instruction is used to determine the address of the pointer stored there. So this is minus hexadecimal 10 RBP. So this is clearly a local variable. So we're loading the address of this local variable into RAX and then moving RAX into RDI, in effect passing it as the first parameter, which is going to be overflown by string copy. So we also know at the start of the function, the return address was just pushed. So at that point, the stack pointer points directly to the return address. Then we push RBP, which subtracts 8 from RSP. As you know, the stack runs downwards, right? So what we get is that RSP plus 8 now points to the return address. Then we move RSP into RBP. Afterwards, they point to the same location, but RSP will still change and RBP will stay the same within the function. So let's instead use 8 RBP as the offset of the return address. So now we know where the important stuff is. The target to be overwritten, that is the return address, is at RBP plus 8, whereas the buffer to be overflown is at RBP minus 16. Now how many bytes do we need to write before we hit the target? Please pause the recording if you want to think about it. So we simply subtract the two from each other, and in this case RBP cancels out. So we subtract RBP minus 16 from RBP plus 8, and we simply get 24. So what is the exploit in this case? 24 bytes of garbage, anything that doesn't contain a null byte, because the null byte will terminate the string copy, and then followed by the new return address that we want to write on top of the current one.